Hi class, we're now on 17.4. We're going to look at acid strength and the acid ionization constant, which is Ka. So acid strength. A strong acid is a strong electrolyte. That means, it means that 100% of the molecule dissociates into ions. A strong base is a strong electrolyte, and all the base molecules form hydroxide ions either through dissociation or reaction with water. A weak acid is a weak electrolyte, and remember that this is only a small percentage of the molecules ionized, while majority of it stays intact. And a weak base is and this is where the equilibrium arrows come in. A weak base is the same. It is mostly intact, and only a small percentage of base molecules form, oh, look at that separated here, sorry, hydroxide ions, either through dissociation or reaction with water, and that's where we see the equilibrium arrows again. So ionic attraction and acid strength. So let's do a review. A strong acid completely ionizes or completely dissociates 100%. A weak acid does not. It stays mostly intact, and there's only partial ionization. And depending on the acid, even those vary on how much partial ionization occurs. Strong acids, strong acids again donate all their protons. 100% ionized in water. It is a strong electrolyte. When we look at the concentration of it, it's really easy because it dissociates 100%. We can look at the concentration of hydronium ions because it is the concentration of the strong acid. So if we have 1 molar HCl, it is also now 1 molar of hydronium molarity. The concentration is the same because it has ionized completely. So we use the brackets, which means molarity. So these are really easy to determine the molarity. Not the same for weak acids. Weak acids, because they stay mostly intact, only a small fraction of the protons ionize. Most of it stays as a molecule, and much less than 1% is ionized. So this means that the hydronium concentration that has been produced is smaller than the concentration of the weak acid, the molarity. So here's some examples of strong acids, and we have HCl, hydrobromic acid, hydroiodic acid, nitric acid, pure chloric acid, and sulfuric acid, which is diprotic, which means it has 2 protons. Examples of weak acids are hydrochloric acid. Oh, excuse me, that's wrong. That is not right. That should say hydrofluoric acid, acetic acid, formic acid, sulfurous acid, which is diprotic, carbonic acid, which is diprotic, and phosphoric acid, which is triprotic. So the strength of the acids, and acid strength depends on the degree of the attraction of the acid ion and the proton. So this means of how strong. If it's a weak acid, it does not give up that proton very easily. If it's a strong acid, the strength between, for instance, HCl, there's not a strong attraction and they separate very easily. Where if it's a weak acid, that does not happen. Acid or base strength is measured by determining the equilibrium constant of a substance reaction with water. This is when we're starting to look at weak acids and weak bases, because a strong acid goes 100%, so the arrow goes in one direction. When we start looking at weak acids and weak bases, we have to look at the equilibrium. So how do we determine the strength of the weak acid and the weak base? And that has to do with the smaller ionization constant K. So we're going to look at the ionization constant K for the weaker the acid or the weaker the base. So this is going to tell us, based on a value, how much of a weak acid we're dealing with or a weak base. The position of the equilibrium depends on the strength of that attraction of the base and the proton. So a stronger attraction means a stronger base or a weaker acid. Okay, so acid ionization constant is Ka. Acid strength is measured by the size of the equilibrium constant when it reacts with water. So the Ka is also the same as the equilibrium constant when we're looking at weak acids and weak bases. So if we look here, we can look at this in 2 different ways. We have Ha, when it comes into contact with water, produces hydronium ions and an anion, or we can just look at the dissociation of the acid. Both of these are in equilibrium. We have the acid that dissociates into a proton and an anion. The equilibrium constant for this reaction is called the acid ionization constant. So the larger the K, it equals a stronger acid. So if it's 1 or above, it's a strong acid. the closer it gets to 1 means it's a stronger acid. And when we start looking at those negative numbers, the bigger those negative numbers, the weaker it is, because that's more zeros in front. So when we have to set this up with the Ka, it's very matching the equilibrium, where we pull the products there on top and we have the reactant on the bottom. And either way, depending on how you look at it, as you can see, it's either hydronium or we're dealing with just the proton. So calculating the concentration of hydronium ions in strong acids is very straightforward. Again, if you know what the concentration of the strong acid is, it's also the concentration of the hydronium ions. However, most of the acidic compounds are weak, so we cannot look at that same way, because most of weak acids stay intact, mostly intact, and only partially ionize. So weak acid ionization is an equilibrium with an equilibrium constant. So let's look at the reaction of acetic acid. So here we have acetic acid in the presence of water produces hydronium ions and an acetate ion. But the reaction's showing this, but majority of the weak acid is going to stay intact as acetic acid. And there's not going to be as much hydronium ions in that are being produced. However, we can still set up the Ka, so we take the products that are on top, the brackets mean concentration, and acetic acid on the bottom as the denominator. So here's a general expression for weak acid ionization. We have either like as on the previous slide, we have either equation here, but this is known, the Ka is the acid ionization constant. So Ha is the weak acid, A minus is the conjugate base, and then we have the hydronium concentration. Here is a list of acid ionization constants. So again, the larger, so if you look for first, here's the name, and the pink, excuse me, hydrogens are the proton that comes off. And then you see the structural formula and the ionization reaction. So this is a pretty good slide that shows you a lot of what's going on. The Ka and the pKa, which is what I'm going to discuss next. And depending on which one, if you understand pKa, it's actually easier to understand than Ka. But my professor in grad school, he only wanted to discuss things with pKa and never Ka. And as you can see, it's just a number with not scientific notation, so it actually makes it easier once you understand it. So if you look here, let's go over this. The larger these numbers are here, the weaker the acids are, because these are all the zeros that have to go in front of this number. So it's further and further away from being a strong, considered a strong acid. So even weak acids have, in a sense, a hierarchy. Some are considered stronger than others. A weak base ionization is also in equilibrium. So weak base, here's an example of ammonia. So ammonia in the presence of water produces ammonium ion and hydroxide ion. And we set this up, instead of a Ka, we now have a Kb. But we set it up the exact same way, as long as you understand that this is a base ionization constant. It's the base that's disassociating, a weak base, and how much of that disassociates with the hydroxide ion. So B is the weak base, and BH plus is the conjugate acid. The acid ionization constants and base ionization constants are equilibrium constants. So we're looking at this as they're also equilibrium constants. They're not separate values. A larger Ka and Kb values indicate more complete reactions. That means that they ionize more. And if they have lower values, then that means that they ionize less. So if we look at some Ka values here, again, the bigger these numbers are, the weaker they are, and the smaller the numbers are, that means the less zeros that are in front. So they're considered stronger, weak acids compared to weaker weak acids, if that makes sense. And then we have Kb values, which stands for base ionization constant. Same applies. We're now dealing with hydroxide. So how much of these weak bases ionize or dissociate? So here we can see same applies. You can look at the values here. So now let's discuss pKa. pKa is also a measurement of the strength of an acid, and it's kind of easier to understand than dealing with Ka. So a pKa depends on the concentration of acid, conjugate base, and proton, or hydronium ion concentration. So it's a number that shows how weak or strong an acid is. Very similar to Ka, but it's actually opposite of values. So measures the strength of an acid, which is how tightly a proton is held by a Bronsted acid. So we look at this here, and a pKa is the negative value of the logarithmic of Ka, which is what I'm talking about right here. And a Ka can be determined by the Ka, and you have the 10 minus pKa. I'm sorry, I actually forgot what this was right now. As I was looking at it, my mind went blank. But you can see that you can go through these to determine. If you want to know the pKa and you have the Ka, you can plug this in. And if you want to know, if you have the pKa, but you want to know the Ka, you plug it in with this equation on your calculator. So this is where they're opposite. A larger Ka means a smaller pKa value, and that indicates a stronger acid. A smaller Ka represents a larger pKa, and that indicates a weaker acid. So let me see if I can explain this. A pKa that's low, it indicates a strong acid. A pKa low value. A pKa that has a high value is a weak acid. Hopefully that makes sense. I found this slide, and this just gives an idea of the scale of what's going on. I, of course, didn't make this slide, but I found it online. Okay, so you can jump from one to the other as long as you know the equation for it. So here, if you want to determine the Ka, you would use this equation because we have the pKa. And here again, we have the pKa. But what if we have the Ka? Then we would use this equation, the negative value of the log, the negative value of the logarithmic Ka. And we can see we can jump back and forth. So if you plug those in, and hopefully you should try plugging them in and make sure that you have these values. So then I have given these values. So you should be comfortable going back and forth. So this would be a good exercise to try and make sure that you have these values. So rank the acids from smallest Ka to largest Ka, or largest to smallest pKa. So Ka, the larger the value, the stronger the acid. And it's the opposite for pKa. The larger the value represents a weaker acid, and the smaller the value represents a stronger acid. So that's why it's easier in a sense to use these values over these values. So let's take a look at the order so we can understand this. Phosphoric acid. So this is from weaker acid to stronger acid. So phosphoric acid has 2.6. Remember, we're starting out with larger numbers. They represent weaker acids, and the smaller numbers represent stronger acids. So this is 2.16. Chlorus is 1.96. Sulfurous is 1.85. Oxalate is 1.25. And periodic is 1.14. So this is why this is kind of easier to use than this one once you understand that. As long as you understand the values and how they either decline or increase. So reactions involving weak acids and weak bases, go to completion. Okay, so even if you have, go to completion even when one of the reactants is a weak acid or weak base. However, it's a little different than what we understand with the strong acid, or, when we talk about this. So one of the products will be a weak acid or weak base that can undergo equilibrium ionization. So this is a good example. Ammonia reacts with hydrochloric acid. Because hydrochloric acid is a strong acid, it will never not dissociate. It will completely dissociate. Pay attention to the arrows. They also tell you what's going on. So here in the presence of ammonia, which is a base, we have HCl. So this is going to completely ionize regardless. And it does. As you see, the proton gets donated, ammonium ion is produced now because nitrogen accepted that, and we have Cl, we have a chloride ion. Now what happens though, if you see in the second one, it's going to be in equilibrium. So the ammonium is going to react with the water, which produces hydronium ions, and ammonia, which is right here. That's what this is talking about. There will be an equilibrium constant. An equilibrium ionization will occur with the weaker base or the weaker acid. Okay, so let's take a look at this. Consider the three generic weak acids, HA, HB, and HC. The images shown here represent the ionization of each acid at room temperature. Which acid has the largest Ka? So once you understand that we're not looking at strong acids, we're looking at weak acids, which means they mostly stay intact and very few will ionize. But we want the largest one, the stronger of the weak acids. So it's pretty easy. We can find one that ionized. Here we have 1, 2, 3, 4. The rest stayed as intact. And over here we have 2. So B, HB, the weak acid HB, is going to have the larger Ka because it ionized more than HA and HC. HA would be the weakest because it only ionized with one, compared to at least this one had two. Okay, so which acid is stronger? If we look at the Ka, remember the values. Look at the values. Then if you have to look at these numbers, do. But the values here tell you which is the weak or which is the stronger. The lower the value here, the less zeros that are in front. So it would be a stronger acid, weak acid, compared to this one. So HF is a stronger weak acid than B. Okay, so let's do some review. The ionization constants Ka and Kb are equilibrium constants for the ionization of a weak acid or weak base. We'll look into this in, I think, the next section. As Ka and Kb increases, the strength of the weak acid or weak base increases as well, which means it ionizes more. Correspondingly, as the pKa or pKb decreases, the strength of the weak acid or weak base increases. So remember, this is going in the opposite value of increasing or decreasing from the Ka and Kb. The ionization constant expression for the ionization of acid or base does not include a term for the concentration of water because pure liquids are never included in equilibrium constants. So just like equilibrium constants, we didn't include them.